This conference will now be recorded.
All right, this is Math 211, looking at section 1.7, the precise definition of a limit. I'm going to be going through two epsilon delta proofs to prove the limit definition for the examples that we didn't get to in class. Hopefully this will help you when you're working through your homework and your instructor choice worksheet. So remember that when we're trying to prove the limit is true by a limit definition, there's kind of a game that you're playing. Someone picks an epsilon greater than 0, and remember that's a neighborhood around the limit that we think it is, which is, remember, a y value essentially on our function. And we try to prove that this limit is still true within a neighborhood of the delta. So we're kind of like, okay, someone gives us an epsilon that's positive, and we have to pick a delta that's positive that then meets the definition of what a limit is. And we'll talk about that again in a second, but that's the goal here. And there's really two parts to this proof. You're kind of setting yourself up for success by finding a delta that is based off of the epsilon chosen. And then you go through the second part, which is just showing and proving that the definition holds. So let me just write out kind of what we need to know for this first one. And here's our precise definition, remember, of a limit. Let's go back up and read that at the very top of our notes, just so we remember what it is. It says, let f be a function defined on some open interval that contains the number a, except possibly at a itself, so it could have a hole there. Then we say that the limit of f of x as x approaches a is L, and we write it this way. Remember, the x approaches a should really be below the limit. And we say that's true for every number epsilon. So not only are we kind of picking an arbitrary epsilon, we're saying this is true for all epsilons greater than 0. There is a number delta greater than 0 such that if the neighborhood around a is between 0 and delta, then the neighborhood around the limit should be within epsilon. Now, we did one of these together in class. In fact, we did two things. We did a graphical one, and then we did one, I think it was example 2. So I'm going to actually skip example 3 for a second because example 4 is a little bit easier to look at. And it says, prove the following limit is true by this limit definition. So the first thing is you have to pull out the correct information from what you're reading. For example, how do you know what's going in these pieces? Delta and f of x minus L. Remember, this was a. It's less than epsilon. That's a delta, by the way. So here's the thing. This is a, because this is what x is approaching. This is your function, and this is what we think the limit is. So we're just plugging those pieces in when we go to write the definition. So our first part of this proof is we're going to be trying to find the delta that's going to work based on the epsilon that gets chosen. So we're going to write out, if someone gives me, because remember this is a proof, we are writing this in a proof statement, given epsilon greater than 0, we need a delta greater than 0 such that, so it's going to have some conditions to it, if 0 is less than x minus this -2 here. So that's actually going to be plus 2. So that's minus a -2, just in case you want to follow along, is less than the delta. Then we know that by the definition we should have, and there's where our function comes in, the absolute value of 3x plus 5 minus a -1, so that's actually going to be plus 1, should be less than the epsilon. Okay, so that's the opening statement. We're trying to find a delta that will meet this condition. So the way we do this is we actually work backwards in this part to make sure we get the success we want in the game. So we say, but, and this is just kind of algebraic manipulation essentially. We would say that if we have this 3x plus 5 plus 1 is less than epsilon, then that implies, if and only if kind of thing, we have a two-way arrow here, that we could actually do some algebra and say that that would be 3x plus 6 inside, less than epsilon. We notice that there is a factor of 3 that can be pulled out, and we'll pull it out in an absolute value because we always want to make sure this is going to end up positive. Remember, because epsilon and delta both have to be positive. So that's x plus 2, and that would just be 3. And you notice that that's x plus 2. That's kind of the desired statement we were looking for here. So if we just divide that 3 over, and since it's a positive, since it's absolute value, it's not going to change the direction of our inequality, we actually get that this is the delta we're looking for. It's based on our epsilon. It's epsilon divided by 3. So that is the find delta based on the epsilon chosen part. And remember, this is for any epsilon greater than 0. So we've actually, if someone says 5, we say it's 5/3. If someone says it's 1/2, we'd say it's 1/2 divided by 3, which is 1/6. So this should work for any epsilon. Now we want to prove that it works. So I'm pretty much going to make you work the correct direction this way. We're going to start with the statement, here's the epsilon, here's the, somebody gave us the epsilon greater than 0, here's the delta we chose, and then we're going to work from this statement, if this, and we're going to plug in our delta, and we're going to prove this. So that shows that it works the direction that it's supposed to in the if-then statement. So if we're given our epsilon greater than 0, and we choose our delta to be epsilon divided by 3, then if we have our statement 0 is less than x plus 2, which is less than delta, that would imply, since this epsilon we also know is greater than 0, I'm going to drop the 0 part because we know we're still greater than 0 here, is less than epsilon over 3. That's just a substitution, which implies I should be able to multiply both sides of an inequality by 3. So 3, and then absolute value of x plus 2 is less than epsilon. We will multiply that through the absolute value. If that's a positive number, that's allowed. It's not allowed so much if it's a negative number. It messes up your inequality stuff. So this is 3x plus 6 less than epsilon. And now you're just going to make the function look like it's supposed to. We're going to turn it back into 3x plus 5 and a plus 1. We're just going to separate it out so that we see our f of x and we see our L. And we've proven that that is now less than epsilon. So that's our f of x, that's our minus L because it was a -1, and that pretty much proves that you took the delta that was based off of what we needed to make this work, and we proved that this statement is true. So the final thing you do in any proof is you kind of restate what you were doing and say, hey, I did it. So this is thus the limit as x approaches it was -2 of 3x plus 5 equals -1 is true by the limit definition or the definition of a limit, however you want to write that. And I like either for you to put a box at the end or you could put QED saying, hey, I finished what I said I was going to. Okay, so that is the one that was similar to one we did in class, so you have that. This one's not much harder, the other one that I picked, but it is, a fraction inside, so sometimes that makes people more nervous. So let me just show you how to work through this one. Same idea, same structure. This is our A, this is our f of x, this is our L. So we're going to be finding the correct delta based on our epsilon first. And be careful, my epsilons look like 3 sometimes, and sometimes my brain wants to write them backwards. So also watch that for yourself. It's very easy to do. So if we're given an epsilon greater than 0, we need a delta greater than 0 such that if 0 is less than, remember this is our A, so x minus 1 less than delta, then our f of x, which is this parentheses 2 plus 4x over 3 minus our L, which is 2, needs to be less than epsilon. But we can work with this because remember we're working backwards to force the success, essentially. And this does get more complicated the more complicated your functions are. Remember, we're doing linear functions essentially. So this is 2 plus 4x over 3 minus 2 less than epsilon implies I could get a common denominator and kind of break things up. So this would be 2/3 plus 4x over 3. I'm going to leave that x on top instead of pulling out to the side. And then I could make that 6 over 3. Just trying to get everything I combined I can. This would be implying that I can combine my like terms. So that would be 4x over 3 minus 4/3 less than epsilon. And then I notice a common 4/3, so I'm going to go ahead and try to pull it out and see if that helps me. And that leaves me with an x minus 1, which is exactly what we needed in this portion, less than epsilon. So all I need to do is think that 4/3 in an absolute value is just 4/3, and then we will multiply that to the other side by multiplying by the reciprocal. You remember that's the same thing as dividing. You just multiply by the reciprocal. So it's going to end up being a 3/4 when we move it over. So its absolute value of x minus 1 is 3 epsilon over 4. Now that's where you can get into trouble because that sometimes starts turning into 33. So I've got what I think my delta based on my epsilon is. I think it's 3 epsilon over 4. Now I'm going to prove it works. Okay, so given my epsilon is greater than 0, we're going to choose our delta to be 3 epsilon over 4. Then we have to start with the correct direction of the definition, which is we start with this. If 0 and then x minus 1 is less than delta, that implies, since epsilon is also greater than 0, we're going to drop that part off, so it's just going to be x minus 1 is less than 3 epsilon over 4. I'm going to multiply both sides by 4/3, which gives me 4/3 absolute value of x minus 1 less than epsilon, which implies that 4/3 x, or 4x over 3 minus 4/3 absolute value around all of that is less than epsilon, which implies that 4x over 3, I'm going to split it to exactly what I did before. This helps us see exactly what the path is. It's 2/3 minus 6/3, and an absolute value is less than epsilon. We're just kind of going backwards here. And then that implies that 2 plus 4x over 3, kind of grouping it back as the f of x, minus 2 is less than epsilon. And that is what we wanted. So thus, the limit as x approaches 1 of 2 plus 4x over 3 equals 2 is true by the definition of a limit. Got lazy there at the end. Box, member, or QED. Either one's okay with me. All right, so that is the end of this section as well. That gets us all caught up, and we'll see each other this week, and we'll be talking about continuity, and we'll be talking about derivatives. So there's some exciting things coming forward. Hope everybody has a great Monday off from all of your other classes, because, you know, calculus is Tuesday.